Here's another example of two-dimensional motion. We have a small boat moving at a velocity. So if I draw a rough sketch, I have our boat headed north at 1.73 meters per second. But now it is accelerated by a river current directed east. So there's an acceleration directed east of 0.75. This is constant. This is a number. There's no function of time. So we know that with that acceleration, this boat is going to start curving east. So this is not straight line motion. The velocity is perpendicular to the acceleration. When that happens, that causes the object, in this case the boat, to turn. So the question here is, it wants to know the new velocity of the boat after 17.3 seconds. Because the acceleration is constant, the kinematic equations, or big three that we've talked about before, are still applicable. But they are only applicable for the x direction or the y direction at a time. So we have to look at x and y separately. Similar to my suggestions in linear motion, when acceleration is constant, I still recommend writing out the variables that show up in the equations. But when we have two-dimensional motion, meaning not a straight line, we want to write out what we know for both the x direction and the y direction independently or individually. So similar to linear motion, when the acceleration was constant, we need to choose an origin, and it makes sense to put the origin right where the boat was initially. That means I am defining the initial position as 0 for both x and y. The final position, this problem doesn't tell me anything about where the boat is finally. It also doesn't ask for it, so we don't know the values to plug in. The v initial, well, it told us the boat was headed north, which means it was moving in the y direction and not the x direction initially. V final is what we're looking for. V final is going to have an x component and a y component. That's what we are going to find. And then the acceleration was to the east, which meant it was all in the x direction and not the y direction. They give us the time. The time is the same regardless, so we can fill that in there as well. Ultimately, we're finding the y velocity, meaning the x and y components. Velocity, remember, is a vector, so we have to account for all of its components. So finding just x velocity or just y velocity is not enough. But that's okay, we can totally find them. These kinematic equations we can use as long as we are using information in the x direction or information from the y direction. So for example, since we have v initial, acceleration, and time, I'm going to just say the vx final is going to equal vx initial plus a in the x direction times time. So this top equation works great as long as we're using x components specifically. Well, in our problem, there's no velocity in the x direction initially. The boat was headed north. But we will end up with an x velocity finally because of that acceleration pointed towards the east. So after this 17.3 seconds, my calculator is telling me 12.975. We will round that to correct significant figures in just a minute. So the boat does have a velocity towards the east, finally, but it will also have a velocity towards the north when I look at the same equation, but for the y direction specifically. We know there's a y velocity initially, but with the wind, or the river current, I guess, rather, the acceleration is to the east. There's no northward or southward component, which tells us that Vy final, the boat will still have a velocity of 1.73 meters per second that is northward. So now, after the 17.3 seconds, the boat has an eastward component of velocity and a northward component. The north one did not change because there's no acceleration northward. Remember, the definition of acceleration is some change in velocity. So not having an acceleration that points north or south means this velocity stays the same. Now, because the problem is giving us magnitudes and then in terms of north and east, it would be most appropriate to give the overall velocity in terms of a magnitude and direction. So we know eastward, the boat will be traveling 12.975 meters per second. Northward, 1.73 meters per second. So the magnitude will be the hypotenuse here. And then we will want to find the angle as well. I'm going to write this symbolically. Pythagorean theorem still applies. Any right triangle. Since I know the components, I'm going to be putting the x component in and squaring it, plus the y component in and squaring it, which essentially, let's see, we have 3 significant figures in this problem, so we will round to 3 significant figures for the speed. So this is the magnitude. So we're not done. We need the angle as well. In this same triangle, we can say the tangent of this angle is the 1.73 over 12.975. Inverse tangent of that gives me to 3 significant figures, 7.59 degrees. So our velocity of the boat after 17.3 seconds is going to be 13.1 meters per second at 7.59 degrees north of east. Because east is to the right, we're going north of that by our angle theta. And so here is our answer. Again, the acceleration being constant means we can use a kinematic equation, but we must use the equation separately and for x and for y. And then we can pull it back together like we did to get this final magnitude and direction.